All right, so let's start with 2.5, rational functions. First of all, what is a rational function, right? We talked about polynomial functions and now rational functions. A rational function, first and foremost, is the quotient, so there is some division happening here, of two polynomial functions. So it's when you divide two polynomial functions. Okay? Just like how this looks here. So you have one polynomial function a of x divided by another polynomial function b of x. Now, once you introduce another function in the denominator, then you're obviously affecting the domain, right? Because the domain of rational functions is all real numbers except those values for which the denominator is 0. Okay? And because of this, many rational functions have asymptotes, and they could be either horizontal or vertical asymptotes, right? All right, do we remember what asymptotes were? These are lines
They cut
that,
off. They never reach the value necessarily.
yeah,
They're
these
cut off,
are lines that the function approaches
but never
but
reach.
never touches, okay? And we say, you know, instead of approaches, we say that the function comes exceedingly close to. But never touches. Right. Okay, so we're going to start off talking about vertical and horizontal asymptotes. And they're each found by different processes. And again, you just need to be very, very, quick at finding these asymptotes. All right, let's talk about vertical asymptotes first, right? A vertical asymptote basically looks like this. Tangents, right, had vertical asymptotes, so we're used to what those are. And then we also have horizontal asymptotes. So let's go one by one. And actually, I want to go to the next page here to talk about vertical asymptotes because it's a little bit more straightforward. Vertical asymptotes are found in the following way. Simplify the function, okay? Then find the zeros of the denominator. But here, we've got to be super careful because there's a little caveat, there's a little thing here. It has to be the zeros of the factors which cannot be eliminated from the denominator. Okay, so that's how you find zeros. All right, so these are, infinite discontinuities only. Now, let's talk about horizontal asymptotes. There are 3 cases for the horizontal asymptotes. Look at this graph here. Look at how that horizontal asymptote looks, right? So like they could look in, any, in a, like a all sorts of different ways. All right. So how do we find horizontal asymptotes? Mathematically, horizontal asymptotes are the limit of f of x as x approaches infinity or negative infinity. That's what it is. So, isn't that what end behavior was, right? The limit at infinity. And to find end behavior, what did we consider in the polynomial function? Did we look at the whole thing? No, we just looked at the term with the highest exponent, right? The leading term. That's what we're going to do here. So it is enough to consider the terms in the numerator and denominator with the highest degree. That's it. And so now, to find horizontal asymptotes, it becomes very, very straightforward. Right? All you do is look at the top, take the leading term, look at the bottom, take the leading term, and you compare them. And then there are three cases, three situations. First, you have lower degree on top, higher degree on the bottom. And in this case, the horizontal asymptote is y equals 0. So for example, suppose, f of x is x squared plus 7 over x cubed minus 3. Okay? All you do is you look at the term with the highest exponent here and here. Lower on top means horizontal asymptote is y equals 0. No questions asked. All right? Next situation is you have equal degree on top and bottom. In that case, the horizontal asymptote is the reduced form of the fraction. So for example, if you have f of x is equal to 3x cubed plus 5 over 2x cubed plus x, higher degree, higher degree. What have we got? Y equals 3x cubed over 2x cubed, right? You don't even have to look at the variables. All you do is take the coefficients and that's it. That's the horizontal asymptote. Because they cancel out. Next, if you have a higher degree on top and a lower degree on the bottom, no horizontal asymptote. So for example, if you have, 3x to the 4 over 5x squared, no horizontal asymptote. Okay. There is one exception. I mean, it's not really an exception, but one other note is that if the numerator has a higher degree by 1, so if it's like x cubed over x squared, there is still not a horizontal asymptote. There is what we call an oblique asymptote, and we'll get to that much later in the lesson. Okay, let's do some. All right. All right, so here, find the domain, vertical asymptotes, and all the horizontal asymptotes, and so on. Okay, so first for the domain. You want to take the denominator and set it equal to 0. But first, can this be factored? Like top and bottom, is there any way to factor and cancel out any terms? No. So let's just set the denominator equal to 0. I add 34, so 2x squared equals 34. X squared equals 17. Take a square root. X is plus or minus root 17. So at those points, I have an infinite discontinuity. So the domain is negative infinity to negative root 17, negative root 17 to positive root 17, and root 17 to infinity. That's the domain. All right. So now let's do vertical asymptotes. This is where you see if anything cancels on top or bottom, which it doesn't. So again, same process. You get that x is plus or minus root 17. These are the vertical asymptotes. Remember that because they're equations, they have to have x equals in front of them. Okay. All right, next, horizontal asymptote. Okay. You have to look at the limit of f of x as x approaches infinity and as x approaches negative infinity. Okay? All right. So now, here's what we do. Go back to the original function. Do you see how they have the same exponent top and bottom? So it's like this is, 5x squared over 2x squared, which means when the x's cancel out, it's 5 over 2. That's the horizontal asymptote. Okay. Questions? All right.
Wait, what was the point of writing the limits?
Because you should always know that, regardless of, even if you're doing it mechanically, you should always know that it's the limit as x approaches infinity.
Okay. So
Right.
do you
Okay.
write that out every time?
No. Okay, so this next one, domain. All right, domain is wherever this, it's all real numbers except wherever the denominator equals 0. So let's see. Let's see where this equals 0. -1. Divide by 2. Take a square root. So x is plus or minus root -1/2. So that's I root 1/2. What does that mean? It's 0 at that imaginary number, right? That means there is no real number which makes the denominator 0. Okay? So we say denominator is never 0. What that means is the domain is all real numbers. Okay? All right, so what about vertical asymptote?
How did you come up with the never zero conclusion? Is that due to the fact that's an imaginary number?
Yes, there are no real numbers for which the denominator is 0.
Right.
Okay? So now, what about the vertical asymptote? Well, this was where you had discontinuities, infinite discontinuities. If you have no discontinuities, then you have no vertical asymptotes. Okay? No vertical asymptotes, since domain is all real numbers. Okay? Horizontal asymptote. Take the highest term and the highest term, same exponents. So we take the coefficients only. So y equals 2 is the horizontal asymptote. All right, questions? Okay, ready for another one?
Can we try one on our own?
You can. And I was actually going to let you guys do this one on your own. Right? So go ahead. Be careful because it looks similar to the first one we did, but there is no square here, right? So go ahead and do this one. I want you to find the domain, horizontal, and vertical asymptotes. All right, I'll give you guys about 2 minutes. So what do you guys think? What's the domain for this one? Ben?
From negative infinity to 17, union 17 to positive infinity.
Absolutely. Okay. Can someone tell me the vertical asymptote? Evan?
I got x equals 17.
Yes. And can someone tell me what the horizontal asymptote is?
0.
Sydney Coppell?
There is no horizontal asymptote.
There is no horizontal asymptote because when you take the highest terms, there is a higher degree in the numerator, so that means no horizontal asymptote. Okay. Let's move on to the next one. All right. So first, domain. Now, do you see how this denominator can clearly be factored? Let's factor this, right? So we have x plus 2 in the numerator, and then on the bottom, x plus 2, I'm sorry, x minus 2, x plus 4. Okay, now, the domain is all real numbers except where the denominator equals 0. Here, the denominator equals 0 at -4 and 2. So the domain is -infinity to -4, -4 to 2, and then 2 to infinity. Okay. What's the vertical asymptote? Now, here's where it's important. Okay? Look at the denominator, right? Do any of these terms cancel with the numerator? They don't. That means both of those terms give you infinite discontinuities. So both of them give you vertical asymptotes. So x equals 2 and x equals -4. All right? So to clarify, the vertical asymptote is where the denominator equals 0. And that's at x equals 2 and x equals -4.
Yeah, got it.
Now, for the horizontal asymptote, this is important. Look at the original function. Right? So here, look at the first term there and the first term there. Do you see how there is a higher degree at the bottom? Because there is a higher degree at the bottom, I can immediately say the horizontal asymptote is y equals 0. Okay, now, because this is pre-calc honors and we need to know the background, let's just, look a little bit more closely. Remember all the limit stuff? What the heck was all the limit stuff? Well, it's because technically in the background, what you're doing is you're asking yourself, what is the limit as x approaches infinity of this x over x squared? That's like, right, when those cancel, what do you get? You get 1 over x. And what happens as x becomes infinitely large? The whole thing will get close to 0. That's where it comes from. Okay, that's why the asymptote is y equals 0. Okay, so it's not just a random thing. Okay, all right. So let's graph some, guys. Did you ever think you could graph these functions without calculators? Well, here we go. All right, so let's graph this first one. We have to figure out domain, asymptotes, and all that stuff. Okay, so first, let's factor. Okay, all right, domain. Where is the denominator 0? at -2 and +2. So the domain is negative infinity to -2, -2 to 2, 2 to infinity. Let's find vertical asymptotes. Look at the terms in the denominator. Do any of them cancel? No. So whichever one doesn't cancel, you set equal to 0. So you get that x equals 2 and -2. Those are your vertical asymptotes. And look, I'm going to put them right there. All right, horizontal asymptote. Go to the original function. Higher degree on the bottom, y equals 0. Okay. Now, we need to graph this. To graph this, what you should also find is the zeros. To do that, you set the numerator equal to 0. What's the numerator here? X plus 1. So x is -1. That's the 0. Okay. Now, I need to tell you guys something important. And this is something that even math teachers I see get wrong, right? It's an assumption. It's a misconception. Horizontal asymptotes are different from vertical asymptotes. Vertical asymptotes are just walls. It's like a force shield. There is no way you can ever cross a vertical asymptote. No way. No way. Horizontal asymptotes are different. Horizontal asymptotes only take effect at the infinities. Its limit as x approaches infinity. That means if you have a horizontal asymptote here, it is only an asymptote at the ends. So in the middle, the graph can cross the asymptote, the horizontal asymptote, 1,000,000 times, as long as it takes effect at the infinities. Okay? So that's an important thing I always make a big deal out of. All right, so let's graph this guy.
Oh, I'm thinking it's because the verticals, it's always the undefined over when it's over 0.
Absolutely.
That can never ever be broken. That would always
Absolutely. Good.
because the
Very
y's is always horizontal, so it can always equal 0.
good.
Algebra.
Precisely.
That's algebra 2 right there, but yeah.
Yep, there you go. Okay, so here we go. I have now 3 regions with these vertical asymptotes, right? 1, 2, 3. So first, when you're going to start graphing, start in the region where the 0 is. That's that middle one, right? So now, look, I have vertical asymptotes on both sides of this middle part. And the graph crosses the x-axis at that point, -1. So there are only 2 possibilities for the graph inside there to look. This is one possibility, and this is another possibility. Okay, there is no other way for that graph to look. So how do you know which one is which? Just pick a point, pick a test point, and plug it in. Okay, so let's test the point. I'm going to pick any value in that middle region. You know what? X equals 0. And plug it into my original function. So when x is 0, what do I get? I get 1 in the numerator over -4. So that's -1/4. So when x is 0, y is here. Okay, now that narrows it down for me. So that middle part looks like this. Okay.
Where did you get the -1 point? Was that another plug-in point too?
No, that's the 0 in green here.
Oh, okay. Well, you gotta find. Oh, if you find the 0, got it.
Mhm.
Yeah, for the. Yeah,
Okay.
got it. Yeah.
So now the left and right points. These graphs are like those video games. You know how like in some video games when the character like goes off screen to the left, it re-enters to the right, right? That's how these are. Wait, meaning if the graph goes off screen on the bottom here to the left of the asymptote, it re-enters on the top to the right of the asymptote. It's like magic, it's a thing, it's a rule. So now it's got to come down here, right? And then to the far right, there is a vertical asymptote. I'm sorry, there's a horizontal asymptote, so it's got to follow that, right? There are no other zeros, so it can't hit the x-axis anymore. So now it's got one option in life. Come down, follow. Okay? And it's the same thing to the other side. When it exits the screen here, it comes back down and it re-enters from the bottom to the other side of the asymptote. Here there is a vertical asymptote. Again, no other x-intercepts, so it's just got to come and follow there. And you can eyeball that. As long as you've got your zeros and stuff, you can eyeball the shape of that. That's what we need. Okay?
Wait a minute. Whenever the shape. So if you have a graph in the middle that's that shape, it will